Welcome back to Survival Modeling in R. We are now going to do a Cox proportional hazards model. And with just the same thing, we're going to do the Trump or Clinton state and the same data and everything else. I'll assume you've worked your way through to this point. If you haven't, you could still go back and load the data, and this should work on its own. And this isn't necessary. I just do Cox pH to let myself know what model I'm using when I go back and look at this for Corona, and I use the Cox pH. Again, we create the same thing, our survival model, which is time to infected status. Everything else looks the same here. And we run our Cox proportional hazard model. All right, and then we look at that, and it comes out and it tells us that yes, the Clinton counties got it sooner because it's negative, right? It got it sooner than the Trump counties, and we could talk about, it's got the EXP here. You can do 1 minus that, and it got it roughly 30% faster, or 26% faster than the Trump voting counties. All right, and we can go through and we can do a very similar sort of plot that we do with the Cox proportional hazards that we did with the simple Kaplan-Meier. All right, and it gives us something that looks pretty much identical, and that's fine. One of the things we can't do in a Kaplan-Meier curve is we could break out a variety of different Kaplan-Meier curves, but we can't add continuous covariates. And we can do that in Cox proportional hazards models. So now I have Cox pH underscore C dot corona, and that's for covariates. I probably could have spelled it out, but we're simply going to run the same thing, and we have added percent African American, percent Hispanic, median household income, percent with a bachelor's or above, median March temperature, and then whether the county was a Clinton or Trump winner. So we go ahead and run that, give ourselves a summary, and I'm going to bounce up here just a little bit so we can see the output. And sure enough, we see that the percent African Americans positive, percent Hispanics is negative, median household income is positive, BA grads positive, average March temperature positive. So all of these things led to later hazards than earlier hazards, later incidents than earlier incidents, except Clinton being an earlier incident and percent Hispanic being earlier incidents. These are slightly the percent Hispanic is not significant, and the rest are. And down here, we still get the Clinton or Trump state being slightly negative. All right, and the exponentiated coefficients are interpreted the same way. You do 1 minus that, and that's the percent increase for a 1% increase in those, or a 1 unit increase, and since they're in percentages, that's what it would be. So we see that those grads running all over the place did in fact lead to higher hazards. And again, this is just another way of looking at the confidence intervals. When you look at confidence intervals here, you've got to remember that it's 1, not 0. So if something crosses 1, it's not significant. It could be higher or lower. If something is like median household income looks like it's 1 and 1, but it's just such a small number, we probably should rescale that so it makes sense. Or median household income is such a large number that when you scale it into these probabilities, it gets pretty small here. But the rest of these are significant. You see Clinton or Trump is below, and this is our Cox proportional hazard model. All right, not too hard to run. They're kind of difficult to actually understand, and how you interpret the coefficients is very unlike regression coefficients. in some ways and very like regression coefficients in other ways. If you've taken a regression class, I'll give you a pointer to about a 6 to 8 hour course on using Cox models if you're interested. All right, we're going to move on a little bit because we've seen some regression models in the literature too, and just how to do those. Again, it's not a difficult how-to. Understanding them's another deal and a much longer course than this one. But this one, it's a very similar formula, except we do, instead of Cox pH, we do SurvReg, or survival regression, and you have to pick a distribution here. And I picked the Log-Logistic because simply we've been using Log-Logistic elsewhere. Many people would start off with a Weibull, but we're going to pick a Log-Logistic. It works well here, and you'll see that in a moment. And we're going to run that the same thing. And we get our summary. And again, the Clinton comes up earlier. Then the Cox proportional average is a little different because the coefficients end up switched on us. But we see this positive there. Again, it's fairly small. It is significant. It's got a smaller standard error. So, and we see that in the graph pretty much. The survival graphs just really don't overlap. And we'll go ahead and do the exponentials there so we can see. So on average, we could look at the graph at about 63.5 days was the average time between the two. And for Clinton, it was about 7, it was a little bit quicker, 7.5%, whatever. Quicker, 1 minus that, and so it was a little quicker. I think I got different numbers when I ran it with an earlier data set, which is what you see here, but that's all right. All right, we can plot that again. We'll replot the Kaplan-Meier curve to have something to plot on top of it, because to plot these, so it's just the same thing, and we're going to create ND for new data, not for no data, and then we're going to predict. And what we do here, we just created a data frame with BA grad and Clinton or Trump equals Clinton. I was playing with using BA grad and doing a multivariate equation. I decided not to do that. Probably should pull it out, but just to let you know, you can put more than one in there. And then we predict based on the model that we have, which is the Log-Logistic, and we predict that for Clinton. Which we just did, and then we recreate the data frame with Trump in it, and then we set our predictions for Trump, and that's P1 and P2. So we use the predict command. This is the object, which is the regLL corona, which is our Log-Logistic model to fit the corona equation. The data we want to predict on, it's a quantile type. There's our Y variable, and now we're going to add lines to that, which is our first prediction, and then the sequence we used in the prediction, which is just 0.1 to 0.99 for the Y. And we add that dark blue line, and we add the dark red line, and we zoom to it. All right. And they fit all right for our Log-Logistic. They're not exactly on top, but certainly the Clinton one fits fairly well. The Trump one doesn't bounce out as far as it could. But it's not too bad, all right? But the parametric models do give us a different fit, and if you want to go down and run the Weibull model for the parametrics, it's actually quite different, all right? And I, again, added the legends at the bottom, which, there you go, Log-Logistic Clinton, Log-Logistic Trump. So that's our Log-Logistic. We were able to do the same kind of models that we were using to predict deaths, and lots of people have found been popular. They tend to have a nice S shape, fit the data relatively well, and that's it. Some people used Weibulls earlier on, and they predicted much quicker flattening. You can look at that. There's some code to run that at the bottom of this script. So we'll add some covariates to the equation, same set of things that we did before. We'll run our summary, and again, we can go see that Clinton led to a greater hazard, and then we had African Americans, a lower hazard, African Americans, Hispanics, median household income, grads, and average March temperatures all going the other way. We do our exponentiated coefficients, and there we go. Everything was very significant in this except percent Hispanic, and that it's probably the one that has received a lot of attention lately due to the meatpacking plants and that sort of thing. But again, the data don't bear it out just in the terms of how long it took for this to happen. Remember, this isn't the number of cases. This is only the time until you actually had an infected case. And so some of these kind of make sense. And some of them, maybe they don't make sense. But they are highly significant. And now you know how to run it. And you have some data. And you can play with it. And that a quick break from the R screens to go over the difference between Cox proportional hazards and the SurvReg, which are also known as accelerated failure time coefficients. To do this on the R screen, you have to spin up and down, and I usually go too fast, and it makes some people dizzy. So I'm going to put them here. I put them in, and I highlighted the percent Hispanic because they're the ones that change direction. Okay, change sign. So percent African American gave us a 1.07 e to the minus 2 scientific notation, which was highly significant, whereas we got minus 2.90 in the log-logistic accelerated failure time. Well, this increases the hazard and decreases the failure time, which is the same thing. So if you fail sooner, that's an increased hazard. Just the fact that the coefficients switch, and they all switch except percent Hispanic. I hope that makes sense. And percent Hispanic didn't because it wasn't significantly different than 0. And with a slightly different model, it was negative, but it was also not significantly different than 0. So it's not unusual to see coefficients that aren't different from 0 flip-flop back and forth between whether they're different from 0 or not. Does that make sense? So each one of these, this increase the hazard for household income, decrease the time to failure. Increase the hazard, decrease the time to failure. Increase the hazard, decrease the time to failure. Decrease the hazard, increase the time to failure. Does that make sense? All right, so whether it makes sense or not, in the long run, we can also do those as the exponentiated coefficients where we can do the -1 or +1. So this one's 1% more likely. They're all very close to 1. So none of these has really monstrous effect sizes. The one, of course, that's the largest is the Clinton or Trump. But in the log likelihood, they're much closer. Okay? So, so I hope this helps. People look at these and then they say, well, that's about 1.8% or 2% more likely per percentage in any given day, and this decreases, right, because it gets lower. So anyway, I hope this helps. You can use these. You have to be careful when you're interpreting the coefficients because, quite honestly, it's a little bit rough, particularly since the models mean different things. But the easiest thing to remember is that Cox proportional hazards are hazards model and failure time are failure time. So the increase in a hazard is a decrease in the failure time. All right, just slightly different angles of looking at the same problem. I hope this helps explain.